Hello, and thank you for being here today. Just want to first introduce myself. My name is David Cifuentes. These are my partners Sydney Palmer and Corey Franck. And today we'll be presenting on the BRO, a burn rate optimizer. We appreciate you being here and listening to this presentation. What it is a presentation on up-and-coming technologies at Hot Air Industries. The first step is that we want to describe the reason for a burn rate optimizer. The Environmental Protection Agency recently came out with a study that indicated that hot air balloon operations were significantly contributing to greenhouse gases, and mandated that all hot air balloon operators needed to optimize and minimize their burn fuel rate in order to reduce greenhouse gas emissions. So that's the reason that we've seen that the market is going towards a burn rate optimizer, and there's currently no technology out there to satisfy that need. As a company, we've decided to invest resources and begin developing that optimizer. The steps that we'll take in this presentation are to explain the development of our current optimizer, including our theory and its current performance and implementation. And then we'll talk about some steps forward.
Yeah, so the way that a hot air balloon operates is on the principle of buoyancy. Which is just, the difference between the densities of the hot air inside the balloon and then the colder air outside. So we developed a force balance on our balloon that you can see here that relates our net force on the balloon, or the mass times the acceleration, which is equal to that buoyant force we talked about, and then minus the force due to gravity and minus the drag force. Those densities are a function of a function of temperature, and which also changes with time. And so we also had to develop or derive an energy balance on our hot air balloon, which is this equation here. You'll notice in that equation this m dot fuel, which is the burn rate. And so, as David mentioned earlier, that's what we wanted to optimize or minimize. And so we implemented this model or these equations in MATLAB, and then minimized both that m dot fuel as well as the error between the input height and the actual height of the balloon. And then the next step for our optimizer was to validate that its results were realistic.
So, an integral step in any model or optimizer is to validate its performance to ensure that it predicts realistic behavior. So let's imagine three case scenarios for a hot air balloon. One in which the balloon is starting at 600 meters and descending to ground level. In that case, we would expect the balloon to accelerate as it descended, and for the burner to turn on to slow the descent, to prevent the balloon from hitting the ground and crashing. And we can see that scenario predicted in our first case scenario here on the top left. And in that scenario, you can see that there are several burn rates. And I'd like to point out the second one here. And the reason it burns a second time is because after the balloon hits the ground, the balloon envelope needs to remain open so that way the passengers can get out of the balloon before they dismantle the whole thing. Now, second case scenario is if the balloon were ascending. We'd expect the balloon to rise to the elevation and remain at steady state. And we can see that behavior modeled in the second on the top right graph. And in that graph, we have an initial burn rate and then a smaller one. And the reason that the second little peak is smaller is because as you go up, the density decreases, which means you need less of a temperature difference to achieve that same change in height. And now, we wanted to understand what would happen to the balloon if we ran out of fuel during flight, which is modeled in our third test scenario down here on the bottom. And in that case, you can see that the balloon does in fact increase its altitude until it runs out of fuel, and then it kind of hovers around steady state as the balloon cools, at which point the balloon begins free fall. And without fuel to control the height and the speed, the balloon will crash. So we were happy to see that the BRO could accurately and realistically predict the behavior of a hot air balloon, and we expect that we can use these results in further research.
In conclusion, we currently have a functional BRO, a burn rate optimizer, and it can be utilized in industry right now with any operator. Any operator could take a computer, use the optimizer, and follow the prescribed burn rate in order to optimize their fuel consumption. But what is the path forward for the company? We could potentially make this a better model by removing some simplifying assumptions that were made in the first generation of this optimizer, including heat and mass transfer correlations and drag correlations. In addition, another huge benefit that can be added to the industry with our product is if we could link the operation of the balloon to this optimizer and fully automate that process. Thank you for listening to our presentation today. We're excited to see the path forward of this new and up and coming technology for hot air industries.